there. Now at this point, we can start looking at and figuring out what's going on as far as this angle goes. And really, to solve that, since we have a time, just like we did here, once we got this time, we're going to have to solve for the y component of the velocity like we did down here at this part. And we would go back to this equation. And so we would say a distance we do know our distance is 16.6. We'll call this 0. I'm sorry, we'll call the velocity original unknown plus 0 because we're saying up until it gets to the apex, which the velocity final would be 0 over 2. And then again, we're going to go with our just to the top time, which is half of total time. And then we're going to solve for our unknown. So I've solved for the unknown with the velocity. Hopefully that makes sense to you. And this gives us the velocity. And again, we want to think about this being on the y-axis. This is everything happening on the y-axis here. So we're not quite done yet, but what we do know is, and let me grab another piece of paper. We do know we have a velocity on the y-axis of 18.04. We also know they gave us the velocity on the total velocity, the resultant, if you will, of 37.2. What we can do then is we can solve for the velocity on the x-axis. Why do we need that? Well, we need that to figure out what happens on the total distance, because remember, distance is completely controlled by that x component velocity. Height and time is completely controlled by the vertical or the y component velocity. We have enough information here to solve this. Just as a reminder, maybe it's easier. I always think it's easier to look at this if I remember that this y component can always be put over here. I'm going to move this up. We can use simple Pythagorean theorem to solve for the velocity on the x component because it's just a triangle. So when you use Pythagorean theorem there, you find that this Vx component is equal to 32.53. And then, knowing the Vx component is 32.53, we can we're going to need to solve this distance on the x-axis. So then we can go back to our equation, velocity equals distance over time. And we can remember that we can always solve that we can say that distance equals velocity times time. And we can always remember that we can add the x component to that in that if we want to. In here, of course, we do. So we're going to say distance on the x-axis, which is what we're trying to solve here, is going to be equal to our velocity on the x-axis, 32.53 times. Now, which time do we use? Well, we want to know the total time. So that would be 3.68. And so we've said that distance on the x-axis would equal 119.71. So that would be, I was misreading my calculator for a second, the distance on the x-axis. The final thing we would need to solve is the angle here. And of course, we can do that using what we've done in the past multiple times. Matter of fact, I don't even think I'm going to do it. I would refer back to when we did that right here. We get down to it. You can always use the this equation, once you have one of the component velocities and a total velocity, you can use that. I'm not going to take the time to show that again, but that's how you would solve for this final velocity. I'm sorry, for the launch angle. I will say doing that got me to 29.01 degrees, which would put us at 29.01 degrees.